Codeforces round 981, problem D, Kousuke's assignment, which is a very nice dynamic programming method that's similar to something we learned in the algorithm class, job schedule. Here is a problem statement. Given an array, find max num of beautiful intervals. And what does beautiful intervals mean? Sum equals 0. Let's give an example. What are the beautiful intervals in this example? So summing to 0, 1, 2, and -3. Is this a beautiful interval? Yes. Also for a -4 is another one. Let's say method 1. If we can get all the 0 intervals, what can we do? Isn't this just a job scheduling problem? Given a set of intervals, job 1, job 2, job 3, and what is the maximum number of jobs that we can schedule where all the jobs are non-overlapping? How to do this? First step, sort all the endpoints. And then, after sorting, we will scan from the left. For example, we take it, but for the second job, at this endpoint, the interval overlaps with the first endpoint. Therefore, we couldn't take this. The third job, it doesn't overlap with the current existing endpoint. So we take it for the last one, and now the current endpoint is at 4. Oh, sorry, the endpoint is here. We overlaps with the current endpoint, so we don't take this. Therefore, the maximum of job is 2. What is the time complexity of this greedy algorithm? Sorting, how long will it take? N log n. And scanning, this is O n. So this algorithm is n log n. But how do we generate all these beautiful intervals? Here is a crucial step. Generate. How long will that take? This is n squared. And why? Because to generate all the intervals, the first element, we can make an interval like this, to the second, to the third, all the way to the ends. How many operations we do for the first element? N operations. And for the second element, we also generate all the intervals. So n times n, we will have n squared number of intervals here. So this method, we get a time complexity n squared, which is not optimal. How can we do better? Let's try another method of dynamic programming. And this will give us a solution of better than n squared. So how to do a dynamic program? The example, let's rewrite it again. 2, 1, 2, -3, 1, -4, and 4. How to do a dynamic programming on this? Let's say dp is equal to, so the intuition is when we are at index I, we find a beautiful interval. Now, if we know what is the number of intervals before this index j here, then what to do? Do we just add the number here? So this is dpj, num of beautiful intervals before j. If we already know this answer, then what should we do? We just add 1 to this, and this will give us dpi, right? So we add this new beautiful interval up to all the intervals before the index j, the I and j. This is the basic idea. But how to find this index j? The intuitive idea is at index I, we check whether the current element is a beautiful interval, which is not. Then we check the next, and then the next, and then the next. So we need to look back to find j, such that the interval j all the way to I sums to 0. But as you can see, this will take n steps at most. So we might be able to loop back n times. This method will give us a n squared solution again, because we start from I equals I in the beginning all the way here. So how to find j effectively? So how to find the left endpoint of the current beautiful interval? How to find beautiful interval fast? The question is this. The answer is use a map. If we know that we can keep track where is the last time we encounter a value, we can use a map to do that. Method 3. So previously we still got an n squared solution with ordinary dp. Method 3, dp plus map. Observe what is special about the beautiful interval. For beautiful interval j all the way to I. For example, 2, 1, 2, -3. If we keep a prefix sum, what will happen? So the prefix sum array, the prefix sum is accumulating the current element from the leftmost starting point. So the first prefix sum is 2. Second is what? 2 plus the new value is 3. and 3 plus the new value of 2 is 5, and then plus the new value is 2. Wait, what's happening here? What are the two values here? 2 and 2. They are equal. And what does equal tells us? Here is a beautiful interval, right? Sums 0. So, and the left endpoint is j, the right is I. So in the prefix sum, j minus 1 is equal to prefix sum of I for a beautiful interval ji. Why is that? Because beautiful interval means the sum is 0. So in the prefix sum, we add a section of sum 0 to it. So it doesn't change the prefix sum. So 2 add a sum of 0 is still 2. Voila! Having this observation, we can create a method using map to get the beautiful interval in O1 pi. So observe for beautiful interval j to I, prefix sum of j minus 1 is equal to prefix sum of I. Here, this beautiful interval 2 and 2 is the same. Therefore, let's keep a map with the value, the prefix value, mapping to the index, prefix index. So here, the prefix value of 2 will have an index of 1, so 1. And how can we use this map to check whether we encounter a beautiful interval? When we encounter 2 again, we can check the map and see, wow, 2 already appeared before. So we can retrieve the index and then directly get where the last 2 is at. So if we have another 2 before, we know that we encountered a beautiful interval. And this is how we build the map. Let's walk through an example. 2, 1, 2, -3, 1, -4, and 4. First, let us build the prefix array 2, 3, and 3 plus 2 is 5. 5 minus 3, 2, 2 plus 1, 3, 3 minus 4, -1, -1 plus 4 is 3. Now, from the example, we know that this is a beautiful interval, sums to 0, and this is another one that sums to 0. Do you observe the pattern on the right? 3 and 3 constitute the interval 2 and 2, also constitute the left and right endpoint of the first beautiful interval. Let us build the DP array. What does DP mean? What does DPI stand for? DPI is maximum number of beautiful intervals before index I. What is the transition function? So if I is here and we find a beautiful interval of this 1, 2, and 3, the left endpoint j is here. So at index I, we try to find the first beautiful interval, which is j, so interval ji, and then we plus the result before j. Therefore, DPI is the answer of dpj, meaning the number of intervals before the left endpoint, and then plus 1, because we make a new interval. Or, if we couldn't find any beautiful intervals, what to do? We just keep the value, dpi minus 1. So we don't increase anything. For this example, dp at index 1, there is no beautiful interval, right? Let's write 0. Here I is 1. When I is 2, dp is what's here? It's still 0, right? We don't have any beautiful intervals. Here 2 and 1, and I equals to 3. We still don't have any intervals. I equals to 4. Now, when I is 4, do we have a beautiful interval? Yes, we do. This 1, 2, 3 constitute a beautiful interval. So supposedly, we should have dp at this index being a 1. So 1 interval. But how can we check whether this is an interval or not? We now use the map. So on the first iteration, although the value is 0, we still record map. The prefix sum of 2 is at index 1. Value and index, prefix map. And for the second iteration, we record map of value 3. What's the index? Index is 2. And on the third iteration, map of prefix sum 5 has an index of 3. And now we check, is 2 appearing before? Has 2 appeared before? Has current prefix value appeared in the map? So the current prefix value is 2. Is it in the map? Yes. So after we find the previous index 1, then we know the beautiful interval is the map value, which is 1, and then the current index, map of the current value, so it's the map value and the current index. In this case, the beautiful interval is 2 and 2, 3, 4, 2 and 4. And afterwards, we will still keep track the map of index of value 2. We update it to the current index 1, 2, 3, 4. And that is why how we get a 1, because we found a previous index. Let's move on to I equals to 5. Copy the values. Do we have a 3 appearing in the map? Oh, there is. And what should we do? We found a beautiful interval, indeed. So we get the index of 2, and we will update the map value, 1, 1. We update the map as previously. The map of 2 is 4 and map of value 3 is 5. That is why. And then for 5, we check the previous dp, which is 0. So the dp value here, all to do is 0. So 0 plus the new interval is still 1. Now for I equal to 6, copying the previous dp values, do we have a beautiful interval here? The prefix sum is -1. Is -1 in the map? No. So we have 0 new intervals. We just keep dpi minus 1, keeping it as 1. Now we record the -1 prefix sum having the index of 6. Finally, for I equal to 7, what is the dp value here? First, check the current prefix sum 3. Is it in the map? Here, yes, we found it. And then update 3 to index 7. So after finding the previous value at index 5, we will check dp5. dp of 5, 7, 4, 5. dp of 5 is 1. And now we add 1 because of the new interval. We get 2. So dp5 plus 1, 1 plus 1 is 2. And this is how we got the answer of 2. So 2 beautiful intervals. What's the time complexity? Since each check is O1, we loop through all the values, which is On. What's the space? We have a dp array of n elements, a prefix sum of n elements, and a map of n elements. So all of them are n. 3n is also n. Yeah, this is the solution of Codeforces assignment. A very nice dynamic programming with prefix sum, also using a map. Thank you for watching, and please leave any comments. Thank you.